Yeah, good morning. Let me demonstrate the last example in this optimization exercise. Now, in this problem, the feed is entering into a flash column. The bottom from the flash column is taken out as a product. The feed consists of propane, N-butane, N-pentane, N-hexane, and cyclohexane. Now, the conditions of the feed are known. The overhead product is going to a distillation column, and the bottom once again is taken as a product. The top is compressed back to the flash column pressure. The flash is to operate adiabatically at 150 psi. Now you are required to set up an optimization problem involving some of these variables. You are required to maximize profit. What is the profit you will be able to get by selling off these two products? So the two products that you are going to get are valued based on N-hexane and cyclohexane. So based on the flow rates of N-hexane and cyclohexane, you will be able to earn some revenue from the process. But in order to earn this revenue, you will have to spend some amount towards the utilities. So the cooling and heating costs in the reboiler and condenser are given, along with the work that you are required to pay in the case of a compressor is also known. So the revenue minus the utility cost that you are able to spend, that you are required to spend, is the total profit that you will be able to earn. And you are required to maximize this profit. Of course, in the first problem, A, by varying the flash pressure between 150 to 250 psi. I'll take up the second part because that also involves the flash pressure along with distillate to feed ratio as well as internal reflux ratio. Now, within these ranges, you are required to find out certain optimizations, right? Now, one issue that you will have to identify in this problem is now what type of distillation column model you will be able to select to run this problem. Now, as you can see, the details that are given here, the flash is operating adiabatically at 150 psi. The column has 10 theoretical stages and the feed stage is on 5. Reflux ratio is given along with distillate to feed ratio. The overhead product or the condenser pressure is known and the reboiler pressure is also known. Now, what type of data, what type of model you can use to represent all this data that is given with respect to the column? Once you are able to identify this issue, I think the rest of the problem should be quite simple. Anyway, as you can see, if I try to use a shortcut distillation model, I'll be able to specify the number of stages and feed location, but not the reflux ratio. Only one of them can be specified. So the moment we wanted to give these two specifications, obviously the shortcut distillation model cannot be used. So based on the type of data that is given, you are required to use a RAD-FRAC model. Okay. Now let us go ahead. So we have a flash column, a distillation column represented by RAD-FRAC, a compressor. Now the feed is consisting of propane, N-butane, N-pentane, N-hexane, and cyclohexane, right? So this is, one second, what is the flow rate? You can assume some flow rate, saturated liquid. Okay, the flow rates are given, right? Propane, N-butane, N-pentane, N-hexane, and cyclohexane. Let me add those list of components that I'm going to add first. Propane, N-butane, N-pentane, and then N-hexane, and then cyclohexane. Right. So having specified the components, now go to the next input screen, choose a property model. Let us select Chavo Cedar. Next, go to simulation environment. Now the first one that we have is a flash column followed by a rad frac model followed by a compressor, right? So these are the three models that we have. Now let us try to connect inputs. So the bottom is taken as one of the products. Now the top from the flash column is taken as the feed to the distillation column. The bottom is the second product that we have. So we were able to connect, let me rename this, distillation bottom product, and this is flash bottom product. Now block B3 is the compressor. You know B2 is, okay. Now let us go to the next input screen. Yeah. We were given, I think it is saturated liquid at 250 psi. Vapor fraction, this should be 0. Pressure is 250 psi. Let me change this to English unit system. And we were given propane 10, 20, 20, 10, 40. 10, 20, 20, 10, 40. 10, 20, 20, 10, 40. Right? Total 100. Next, we were able to specify stream 1. Now we are required to specify the flash column. I think that is block B1. Now duty 0 because we wanted to operate this under adiabatic conditions. The pressure at which the flash column is operating is 150 psia, right? Say next. Now equilibrium, number of stages are given as 10, condenser, total condenser. Distillate rate, reflux ratio I think is given as 1. Distillate rate is given as 0.5. Reflux ratio is 1, right? This is 0.5. Next. Yeah, 10-1, feed is in fifth stage. Okay, next pressure, condenser pressure is 50 psi. Stage 2 pressure. Okay, so because there are 10 stages, the pressure drop is taken as 0.01. So 10 into point, I think this should be zero point 0.1. Right. So next. Now this is the compressor. Let us choose isentropic. Discharge pressure should be equal to 150 psi. The same pressure as that of the flash column. Now we have not yet gone for optimization. Let us first look at whether the problem has been satisfied. Now you can see that's okay. The liquid phase, I think in the compressor, when you compress, probably some amount of liquid is happening. That could be the error. We can easily remove it. Now you can see the convergence tail stream, converging tail stream is 6. So this is taken as the recycle stream. So while solving the flash column, we don't know what is the input stream, second input stream to the flash. That's why it assumes and then converges, iterates till the block is converged. So we have condenser duty and reboiler duty in terms of BTU per hour. And we have the work, I don't know whether it is in HP. Yeah, work is 1. Now let me also go to the compressor and say valid phases should be vapor liquid. Okay, let us reset. Okay, let us look at the stream summary. So now out of 10 lb moles, stream 5, we were able to get very small amount of propane, small amount of N-butane, small amount of N-pentane. What is the product? N-hexane. So small amount of N-hexane and cyclohexane. Where is that happening? dB. Yeah, this is the distillation bottom. So 5631, 3.24, right? So we are required to calculate the profit that you are able to get will be based on this. In fact, okay, so FB, right. Let me modify this problem. So let us now resort to optimization. Calculate the total amount of profit that you will be able to get from the profit, the revenue first. So revenue is going to be based on N-hexane and cyclohexane values in both flash column bottom as well as distillation bottom. Say new. NH in flash bottom. It's a stream variable. Mole flow. Stream is FB. N-hexane. Let me just verify that is N-hexane and cyclohexane. Okay. Then the other one is CHFB, cyclohexane flow rate in flash bottom. Again, it's a stream variable. Mole flow. Distillation bottom. Component is N-hexane. And then NH, sorry, this should also be FB. So these two, NHFB and CHFB, represent the molar flow rates from the bottom of the flash column. Similarly, NH in the dB, N-hexane in the distillation bottom. Again, it's a stream variable. Mole flow. Now the product stream is distillation bottom, N-hexane. Similarly, cyclohexane in the distillation bottom product. It's again a stream variable. Mole flow. Distillation bottom. Component is cyclohexane. Now we also have three more duties. Condenser duty, block variable, block is B2, the distillation column, condenser duty. In BTU per hour. Okay. Next, reboiler duty. Again, it's a block variable. Block is B2. Reboiler duty. And finally, network. This is also a block variable. Compressor. Variable is network in HP, right? So what is the objective function? Let us propose that objective function. So 0.1 into maximize 0.1 star capital X NHFB plus NHDB. So this is the total flow rate of N-hexane coming out from both the products. Similarly, 0.2 into plus 0.2 star CHFB plus CHDB. So this is the total revenue minus condenser duty into 1 into 10 power minus 6. You will have to check up the consistency of your unit system minus reboiler duty star 1 e power minus 7, I suppose. Yeah, 1 into 10 power minus 7, $0.02 per HP minus 0.02 star network. So this is the total revenue that you are going to get. Now, in order to get this, you are supposed to vary 3 variables. The first variable is block variable. Block is B1 flash column, and that is pressure. You are required to vary this between 150 to 250 psi. And the second variable that you will have to vary is again a block variable. Block is B2. Variable is molar reflux ratio. This is varying from 0.4 to 0.7. Right? Next variable that you are going to vary is again a block variable as is given in the problem statement. Block is B2. Variable is distillate to feed ratio. Molar ratio of distillate flow rate to feed flow rate. This is also varying from 0.4 to 0.7. Now let us go ahead with this problem statement. Run the simulation. Okay, we have specified the block B1, B2, B2, molar reflux ratio, D2F, distillate to feed ratio. Let me check up that block. Yeah, reflux ratio is given, distillate rate. Okay, let us take distillate to feed ratio as 0.5. Sorry. Reset. Now, unless you provide an initial estimate for some of those variables, you will not be able to vary. I think this you might have already observed while performing design specs. Because the distillate to feed ratio is not available as one of the initial specs, we were not able to run the problem. Okay, let us not worry about some of those errors. I think you can have a look at them at your convenience. Now you can see these are the flow rates. We were able to, these are the initial values, so we were able to manipulate those variables. And at these values, the profit is maximized. So you can see the condenser duty starting with minus 154, reboiler duty is 101, network is 0.35. Because the condenser duty and reboiler duty are given as negatives, because you are trying to add. So what is the optimization value? So the objective function results. Okay, let us look at report. Now let us look at the variables. What are the variables that we have? We are varying P1, P2. So let us look at those values. Sorry. At what values of those dependent variables we were able to get to a convergent solution. So what should be the block pressure of, see, remember, we gave 150 psia. So the same pressure, the lower the pressure, the lower would be your compression costs probably. And the reflux ratio. Let us look at these results. So heat duty, bottoms to feed ratio. Okay, balance split fraction. So you can identify the distillate rate 0.5 was given, but the input is coming at the rate of 100. So what is the distillate to feed ratio? 0.12. Sorry, the distillate rate, this is final values. That is condenser. Reflux ratio is given as 0.7, right? And what is the distillate to feed ratio? Distillate to feed ratio is given as 0.54. So two variables are at their bounded solution. 150, that is with respect to the flash column pressure, the lowest of the range that we are varying. Similarly, reflux ratio is at the highest, 0.4 to 0.7, but the distillate to feed ratio is 0.4 to 0.7 is the range we have given, but it has been optimized at 0.54. So the objective function has been optimized when the distillate to feed ratio is 0.54. In fact, if you are interested, you may be able to run this problem with each of these variables as separate optimization problems and try to combine them and try to see whether there is any variation when you try to vary all the three variables at once. As is required in this problem, you are first of all required to solve the problem with only flash column as one of the variables. Let me also demonstrate having done this only with flash column. I would like to vary this with respect to only flash column pressure. The first one is pressure of the flash column. So let me remove these two variables. Yeah, let us reset and run once again. Now you can see what is the flash column pressure only when you are trying to vary the flash column pressure. And once again you can see the pressure in the flash column is between 150 at 150 itself. Vapor fraction is 0.211, right? So the flash column pressure is not going to affect. So the variable that we are starting at 150 itself probably is all right. Now why this is 0? Now let us look at this result. Yeah, 0 means it is giving network required is about 0.324 HP. So in this way, you will be able to run the problem with each of these variables as single variable while trying